There is no doubt that the future of space exploration will need extraordinary amounts of energy. Solar and fission have always been the preferred energy source for space missions and will continue to be for many decades to come. Fusion will play a role in a not-so-distant future, but if we really want to leave our solar system, we will need something way more powerful. And that is something that only antimatter can provide. Hello everyone, Subject Zero here. In 1928, Paul Dirac made a remarkable prediction. While studying how particles behave at speeds close to the speed of light, his equation that described this phenomenon would always yield two solutions. His key insight was to understand that the second solution was about something real, something that he would describe as being the anti-counterpart of matter. Like for every electron, there is an anti-electron that behaves the same way as the first one, however, with opposite charge. Surprisingly, only 4 years later, Carl Anderson was able to observe something quite unusual with his cloud chamber experiment. He was one of the first to observe what would later be called the positron, or antimatter particle, on August 2nd, 1932, which is forever captured in this picture. A cloud chamber is a particle detector designed for the visualization of the passage of ionizing radiation. The chamber consists of a sealed environment containing supersaturated vapor of water or alcohol. The energetic charged particles interact with the cloud by knocking off electrons during collisions, which results in these trails that you see in the video. In Anderson's case, he also was applying a magnetic field to the system in order to cause particles to curve according to its mass-to-charge ratio, so he could study the different particles. And this is how he got this picture. For untrained eyes, it is hard to spot the anomaly, but what is really happening here is that all particles follow a distinct path that can be assessed mathematically in its trajectory. However, in this picture, the particle in question managed to move in the opposite direction of the magnetic field while behaving as electrons with the same mass and speed. After much research and ruling out the possibility of this particle being nothing more than a proton, Anderson finally came to the conclusion that this must be what Dirac had predicted a few years earlier. I must address that Anderson was not the first one to observe this phenomenon, but he was the first to publish his findings, therefore leading him to win the Nobel Prize in 1936. 90 years later, and we are finally starting to be able to make antimatter. Well, good enough quantities for at least 1,000 seconds. When antimatter comes into contact with normal matter, they annihilate each other and an enormous amount of energy is released, following Einstein's equation E equals mc squared. Just to give you an idea of how much energy you get from this, if you have 1 gram of antimatter coming into contact with 1 gram of matter, that is equivalent of 43.02 kilotons. That is more than twice the power of the Fat Man nuclear bomb dropped in Nagasaki. If we had 2 kilograms, 1 kilogram of matter and 1 of antimatter, then we are talking about 43 megatons, or really close to the most powerful bomb ever detonated, which is the Tsar bomb, which released 50 megatons, or 210 petajoules of energy. Side by side, and you can really see the difference. And that is not all. For the bomb to release its full power, you need a series of triggering methods, while matter-antimatter only needs to touch each other. But enough with destroying cities. As you can see, the amount of energy stored in the system could be used to power the world, and that means with only 5,556 kilograms of matter-antimatter. This is enough to provide energy to the world for every single need throughout the entire year. In contrast, according to worldnuclear.org, the world's nuclear power reactors require 65,000 tons of uranium per year to generate only 400 gigawatts of electricity. But before you get scared of this stuff, just know that we can't make much of it anyway, which is a huge problem. Currently, the only way to make antimatter is by smashing protons against a wall. But this is not just any wall. It is a wall made of iridium, among other elements. First, protons are accelerated in the linear accelerator, called LINAC. This machine is fundamentally different from the rest, where it uses radio frequency cavities to charge cylindrical conductors. Each cavity is driven by a high-power klystron, which is a tube containing electron beams. The electron beams are intensity modulated to a frequency of 400 million oscillations per second. Because these cavities oscillate at the same frequency, the time each particle arrives at these cavities is important in order to get the beam with the right energy. Protons with right amount of energy will not be accelerated further, and in contrast, protons with slightly different energies will either be accelerated or decelerated, reaching the desired energy. These particle beams are sorted into packs called bunches. When the bunch is ready with the right energy of 50 million electron volts, they are injected into the proton synchrotron booster, which further accelerates the bunch to 1.4 giga electron volts, so they can be injected into the proton synchrotron, PS for short. The reason they introduced this booster was to increase the number of proton bunch that could be accepted into the PS. Before the booster was introduced, linear accelerators were not powerful enough to get the protons at the energy level required for the PS. With the booster, there can now be more than 100 bunches being fed into the PS in one experiment. With a circumference of 628 meters, the proton synchrotron further accelerates the protons to 26 giga electron volts. Once the level of energy and speed is reached, the particle beam is released, hitting a target made of iridium at almost the speed of light. These collisions create a multitude of secondary particles, including antiprotons. But the problem is that most of these antiprotons disappears within nanoseconds, and they continue to do so even after some of them make it through. The main problem is at this point. The most effective method of capturing antiprotons is by converting whatever smashed and got through the wall back into a bunch and decelerate them. This is where the antiproton decelerator comes into play. The AD is a ring composed of bending and focusing magnets that keep the antiprotons aligned on track. At the same time, a strong electrical field is applied to slow the particles down to about 1/10 of the speed of light. It is at this moment that the antiprotons are ready to be stored and experimented with. So far, they were able to hold on to antiprotons for 1000 seconds, or a little over 16 minutes. I know it sounds cool and all, but all they are able to make in 1 year with the machine running non-stop is 100 trillion antiprotons, which is not enough to power or blow anything up. Just to give you an idea, it would take 6 billion years to produce 1 gram of antimatter that way. That is a little less than half of the age of the universe. But things are about to change because CERN will significantly increase its antimatter production capabilities starting in 2020. The extra low energy antiproton decelerator, ELENA, is the answer to the problem that I talked about earlier. You see, just like fusion, we only know how to make antimatter with brute force methods. Even though antimatter is actually emitted off of large decaying atoms, and just like Anderson's experiment, they can easily be spotted with a cloud or bubble chamber. Capturing them requires strong magnetic fields in a complete vacuum, or else they will disappear. The goal with ELENA is to achieve a more powerful cooling and deceleration of antiprotons, something that is not possible with current machines. With the setup that they currently have, 99.9% of antiprotons are lost due to the degrader foils used to decelerate them. The new machine is equipped with a beam cooling system that is more efficient and is able to handle larger loads of hydrogen, which increases the capturing yield tenfold. It may not seem like much, but this is a crucial step. Increasing the production amount will allow scientists to fulfill more experiments, like the gravitational behavior of antihydrogen at rest experiment. Up till now, it was not possible simply due to the low quantities available. This is important because the G-bar experiment will finally give us a light on how antimatter behaves with gravity. Is it attracted or repelled by it? How antimatter behaves with gravity is still a mystery, and so far, no experimental direct measure has ever been successfully performed. However, scientists will most likely answer this question within the next few years, after ELENA is fully commissioned and ready to go. And that is not all. This machine will also make it possible to deliver beams almost simultaneously to 4 other machines: A-Trap, Alpha, Asakusa, and G-bar, drastically increasing the yield of experiments. Now, instead of taking decades, we might have all the answers we were looking for in the next 3 years. At least we should hope that. Alright folks, that's it. We're done here.